Good morning. Hello, everyone. Thank you, Andres, for the introduction. It's not 250 patents in embedded security. I'll get to that. This is me. I came up to hardware security in an unusual way. I started life off as a mixed signal circuit designer back in 1989, place down the street called National Semiconductor. I've been at Rambus since about 1998. I've had at least 3 jobs there. I think maybe like 4 or 5 actual jobs there. Currently working in embedded security. I just wanted to highlight one of the coolest things I ever built. Are there any SPICE people? Does anyone actually ever use SPICE in their actual job? Cool. All right. One thing that like SPICE, if you're running a transient simulation, like can't do is actually generate random numbers. You can't just say, I want a waveform and I want it to be random. It's like SPICE is like, you can't have random in a simulation. It turns out you can. I built a random number generator for a project and sort of stumbled into it by accident. It's chaos based. It generates random numbers in a simulation, which is like really weird. It's either like a quirk of the simulation or the matrix is real, right? If you wanted this, I have a SPICE deck. Hit me up on email. I'll shoot you a SPICE deck. It's entirely behavioral models. You don't need a standard cell library or anything. And it generates random numbers, which means you can now generate like random signals to actually, I don't know, fuzz something. You could actually stick noise in your PLL if you needed random noise. Anyways, it's really cool. I think it's really cool. Hit me up. I'll send that along to you. Right now, as I was saying, my current job, I'm in the product management side of things. I primarily focus on, I used to focus on anti-counterfeiting products. So those satellite TVs that John had mentioned. Yeah, cryptography research is now a subsidiary of Rambus. Cryptography research also, of course, very serious hardware hackers in that space. And then they came up with some countermeasures, licensed them to a lot of manufacturers. I took over some of that for when we were in the, printer security space. I don't know if you know that, but some printers actually have security chips on them. Yeah, okay. I was in the business of actually selling that, and this talk is going to tell you everything that's actually in there. All right. I currently focus on U.S. defense, which kind of matters. It's an important market for secure silicon. It's also an important market for reverse engineering. So this talk, when I was putting it together, I had a very boring abstract at first, but I put together an entire new presentation. I wanted to talk about reverse engineering. So then I had to come up with a term for like, well, what's the opposite of reverse engineering, right? So I'm going to call it forward engineering, right? So there's always going to be a talk about forward engineering on this and reverse engineering. And why do companies do forward engineering and build security chips, right? There's primarily 4 reasons why you want to put anti-counterfeiting countermeasures into your chip. And one is, of course, you're just trying to protect revenue. That's almost always the biggest concern, especially commercially. There's also brand protection, which is important if you have a battery charger that explodes and because it's a knockoff, but the knockoff had your brand name on it, it doesn't look good for you. Product safety, things blowing up. But also national defense, huge issue for actually knowing that a chip in a board in a system that's protecting a U.S. or allied warfighter is actually what it says it is, right? So there are serious motivations to prevent reverse engineering. There are also some really decent motivations for succeeding at reverse engineering, beyond just like technical curiosity or protecting bugs or making it better, right? There are plenty of companies that are just saying, there's lots of revenue to be made on this. And I just pointed out, like, for example, today I went and grabbed some numbers, printer consumables. So post-purchase printer consumables, $30 billion a year in post-market consumables. Rechargeable batteries that have some sort of authentication, another 20 billion, medical devices, things like wands and sonogram probes, that kind of stuff, another 10. There's $60 billion to be made in this post-consumable market. And sometimes those consumables, like ink, are staggeringly easy to make, but there's a 20-cent chip, and I got a little picture of what those chips it's a glob top chip. There's all of 4 pins. It's wire bond. That chip, that little 20 cents is expensive. More like 15-cent chip is the only thing preventing motivated adversaries from going after this market. And it's really difficult from the forward engineering side to put countermeasures into that chip, keep the cost down at 15 cents. That's actually going to resist that motivation for $60 billion market access. I crossed out brand protection, product safety, not so important, reverse engineering, but also national defense. I mean, my national defense is my adversaries, not their national. I think of them as adversaries. They think of it as national defense, right? So it's happening on both sides. But also design recovery. There are times that a system, especially in defense-based systems around the world, are put into production. They're classified designs. They are end-of-lifed. The entire database is destroyed. It's apocryphal. It didn't actually happen to the Saturn V, but there was a story once that the Saturn V can't be rebuilt because all the design files for it were destroyed. And if you want to actually figure out how to rebuild something, you have to reverse engineer it. So there are reverse engineering labs that are just out there to help people recover what their design was so that they can reproduce it. Anyway, so I'm going to give a talk here about how security chips are built. So again, forward talk on the top, reverse engineering talk on the bottom. There was a wafer that got awarded out, which is great. I love wafers. Here's how it actually moves, right? You start with a design. The design turns into GDS. GDS gets dropped onto a wafer. Wafers go through packaged parts. And then those things end up into a board system. So how would you, what is the easiest ways to attack this? Well, that's a small wafer. I think that was about a 6-inch wafer. Wafers are actually closer to 12-inch, 300 millimeter now. Suppose you were doing an anti-counterfeiting chip. It's a relatively small little thing. It's about 2.5 square millimeters. So if you take the effective area on that wafer divided by 2.5 millimeters, you're getting about 28,000 die per wafer. Wafers aren't manufactured one at a time. They're put on a tray, usually 25 at a time. So 25 wafers, 2.5 millimeters, all of that size. Suppose that all of those chips are protecting a system that could ship at $200 per board per system. So one tray of wafers is actually affecting the effective market value of $140 million for a single tray of wafers. All right. You, as a reverse engineer, want to be in this business. There's $140 million on the table if you can get that design. Thanks for starting this. Show of hands who, at some time in your life, maybe even today, but sometime in your life, or maybe somebody you know, let's go with that. Somebody you know, right, who would be working in a foundry that has access to those 25 wafers and for a cool $1 million would walk that product out the back door. 10 million. All right, show of hands for 10 million who would do it. This is a bargain of an investment. Basic theft. Don't overthink this. There's a lot of, if you're actually building one of these chips and it's fully enabled from the day you ship, someone's going to steal it. So how do we protect against that? Supply chain security is as important as physical security. The way the supply chain security works, and this was developed by the CRI people, is that you put keys hidden into the netlist at the design, at first electrical touch, wafer sort, you authenticate against those keys, you put in more key material, that moves on to final test. Final test authenticates about what was done in the netlist, what was done at wafer sort, and you're gradually authenticating and putting in more key material, and you're walking the life cycle up. So it starts completely disempowered until it finally goes on the system where it's finally activated. So if it's stolen in anywhere in the middle, your adversary just gets stolen silicon. They don't actually get fully functional silicon. This works. This is done all of the time. What actually happens is that parts can now you can recover a discard and find completely functional silicon that has been usually fully enabled. You can then remanufacture those things and reintroduce them into the marketplace. This does not protect against remanufacturing. How do you prevent remanufacturing? That can actually be done if you're actually tracking what I call the provenance of a chip. Like, where was it wafer sorted? What kind of system was it put in? And if you actually have like chip 2319 and it ends up on cartridge 5634, if chip 2319 starts turning up in other places around the world, you would know if you actually had a cloud-based verification system that you could actually assert going, that's not actually the chip, right? That's not 2319. That's a fake 2319 that got copied from a design. And if there's 27 copies of chip 2319 in the world, you know which 26 are compatibles and which one's the actual authentication one. This is really hard to do at scale commercially. We're working now on a project with one of the national labs to make sure that this is done for U.S. microelectronic systems. All right, so that's my talk about supply chain security. Please keep it in mind. It is an important part of getting all of this right. So I'm going to back up a little bit. How do you actually secure an authentic chip? Suppose you were actually building a chip and you wanted to secure it. Suppose you actually had a secure chip and you wanted to attack it, right? Two sides of the same question. One of them, an authentication chip is staggeringly simple. As a lot of you probably know, there's non-volatile memory on a chip, or there's there's a puff circuit on there, which is like an NVM that you don't have control over. There's a secure core that's going to do some sort of protocol against that data. That's all that's really in an authentication IC. Sometimes you drop those chips into other high-performance SoCs. As John mentioned, you might do this for a state-of-the-art AI chip that you don't want ripped off. You might drop some authentication in there. There might be a root of trust that's doing some of this. Or you're just actually trying to secure one of those products in that $60 billion market that I mentioned. If you're building a compatible chip authentication IC, usually the easiest way of doing this is to find something off the shelf. There's plenty of 32-bit MCUs out there. They have embedded flash. You can write your own code for it. It's also a 4-pin device. It supports a variety of physical protocols. They're staggeringly inexpensive. And if that's your only gap to getting into a $60 billion market, what you need is the key material out of that chip. You don't need all of it almost all of the time. You need the key material. So a lot of this talk is going to be focused on how do I get key material out of that little chip on the left so that I can put it on the orange chip at the bottom and make a lot of money. Any questions yet? I'm just going to keep going and talking real fast to try to get this done on time. Cool. There's Q&A at the end. So, all right. This is the basic practical magic to protect authentication. It's all about challenge response, right? There's a verification host at various places during manufacture. This might be automatic test equipment when you're manufacturing the chip, right? I said there was a netlist keys. How do you know that the chip actually has the netlist key? There's some sort of challenge response protocol. I'll talk more about that. You might have a host or cloud verification in situ. This would be the printer, for example, talking to a print cartridge. There might also be a companion chip in situ, which is great because sometimes the printer actually uses an Oracle chip that's closely partnered with it, and that Oracle chip and the prover chip actually know each other, and so the printer can offload its verification to a separate chip. Also, RMA, something shows up and it's broken, and you want to put it back into a secure debug state. You better have some key material in the chip that allows you to activate that secure debug state. So challenge response is essential to all of this. And as is going to become clear, as most of you already know, authentication has many attack surfaces that your adversary can exploit. So this, I apologize for the font size. This is what a usual challenge response looks like when a authentication chip or authentication of any sort is connected to a verification host, right? The host is going to pull some sort of certificate or device ID from the chip. It's going to send it a challenge. The secure chip is going to process that challenge and return a value. That's the response. And that assuming that the response is correct, it's then going to enable some sort of trusted execution, like printing. There's a lot of attack surfaces here. There's a lot of specialties that a lot of you have. Chris Sarnofsky goes after this in a very, very interesting and very specific ways. A lot of you have toolboxes that are as specialized. Bring that, because there's a lot of attack surfaces to go after these pieces. I'm going to pretty much talk about all of these attack surfaces in some way, and there's a lot of techniques. I can't cover all of them. Nobody could talk about all of them in one talk. At least nobody would have to suffer through it. And I mean, my dog will listen to me when I start talking about this stuff. But in general, right, there's a lot of passive attacks, things you can do without taking the chip off the board, really. As long as you have physical access to the chip, sometimes even like remote access. A lot of these software attacks could be done even remotely. But there's passive attacks that you can go after a chip Really inexpensive, not a lot of specialty needed. You can move to semi-invasive attacks. This is when, like what Chris does, that you start like messing with the environments of the chip. You start causing glitches. Maybe you're injecting faults with lasers. Ooh, chemistry and lasers. Love it. Fault injection, laser probing. You do some some software injection. You go after the scan signals, all that good stuff until you get up to the fully invasive attack. And really, if you're doing forward engineering, this is success. Right? This is what success to reverse engineering looks like, is that you're forcing your adversary to actually do these expensive attacks. There's a lot of material prep. There's a lot of expertise. You tend to break the silicon that you're working with, so you need a lot of samples. There's a lot of things here. They're incredibly effective. They're also really expensive. So sometimes this pushes it up to nation-state attacks, where things over on the left can be done by everybody in this room, except me. All right. There's a lot of things I'm going to choose to not talk about today. I looked through the agenda. A lot of these things are in here. I'm not going to talk much about DRAM. If Rowhammer's going to mess up your data in DRAM, that's on you. Everything in DRAM should not be trusted. It should always be both private and authenticated. Inline memory encryptors exist. Everyone should be using them. I'm not going to talk about hardware Trojans because I don't know what they are. I think the person that came up with the concept of, it's one of those boogeymen that's under the bed that no one's ever seen it, but it's like feasible. But I think the person that's like thinks it's feasible. Does anyone remember ruby die cut when you were actually making that old? Okay. Back in the day when you were actually doing GDS, you did it on big ruby paper on big light tables. There was always white space on the chip, and people are looking and saying, well, what if an adversary puts a hidden MCU in the white space on a chip? This was long before extreme UV lithography and multi-pattern immersions and all of that stuff. So hardware Trojans have never been seen in the world, and I'm not going to worry about them until they actually are. Laser voltage probing, really cool. It's a semi-invasive technique of actually seeing the electrics. It has this huge limitation that you can't actually see ones and zeros. What you can see is a transition. And you don't really know if it's a 0 or a 1, so there's pretty simple countermeasures to making sure, if you have a bus of signals, 32 bits, don't reset them all to 0, right? Have some asynchronous set flops and some asynchronous reset flops, and don't tell anybody which bit it sets to. And then your adversary doesn't know. They see transitions, but they don't know. Did it start as a 0 and go to a 1? I mean, if you're just resetting to all zeros, you're giving it away. I'm not going to talk too much about anti-tamper sensors. That's going to be in a later part of this when I do talk about tamper-evident puffs and how they work with sensors. I'm not a big fan of a lot of sensor technology. It's like, I was thinking, you're walking past the driveway of your neighbor at night, and a spotlight comes on, and you're thinking, that's what an anti-tamper sensor is. And you can imagine a thief who's going to break into that house, and they're like, oh no, a light. I can't rob that place without this rock. I don't believe in a lot of sensors. They're too easily deactivated. Camouflage logic, I'm not going to talk about that. You can Google, this is crazy, speaking of patents, you can Google for camouflage logic patents, which is really ironic because camouflage logic is supposed to be invisible, and you're actually trying to make it impossible to actually detect, is it a 3-input NAND gate or a 2-input NAND gate? And well, if it's impossible to actually know, how do you know anyone's infringing it? Why would you have a patent on it? One of the interesting things about camouflage logic, too, is that some of those patents are held by companies that specialize in reverse engineered compatible products, because they're building a compatible chip, and they don't want the tier 2 reverse engineering companies to rip off their designs, which are less protected than the original design. So they're camouflaging their solution before they put their compatible part in the market, that's a whole talk right there. I'm also not going to talk about logic locking. There's way too many attacks that go after logic locking, and some of the machine learning models and the AI pieces, the satisfactory solution. Anyway, there's a lot of attacks that go after logic locking. I'm not a big fan of it, but there's ways to make it work. Question in the front? Oh, logic locking mean it's like turning a combinational circuit into an FPGA. You give it a 1024-bit vector, and it configures it to now run correctly. So it's conceptually similar to FPGAs that you load a bit file and then it operates correctly. You do it with just a form. So when you're seeing this code, when you're seeing this reverse netlist, you have absolutely no idea what the logical function is until it gets that configuration vector. And now your adversary has to go after that particular vector. And that's a really good question, that a lot of these attacks, and they all assume that your adversary is not as motivated as they are. A lot of the countermeasures are a little lazy, and they assume your adversary does not have, a $60 billion market to go after. So, okay, again, show of hands. Suppose that you're going after a reverse engineering chip, right? And there's a 1024-bit configuration signal, and you can't have a compatible part until you go and physically measure all 1,024 signals. So you got a small team of people, $10 million. Shows of hands. Who's willing to run that team to take 1,020? No one. All right, nobody. All right, well, we got 2 people. There's 2 or 3 people that are actually going to be willing to. It seems like a lot of work. It really isn't, but it's feels impossible. When you feel about logic locking, some people go off and they're like, nobody can clone it. And I'm like, yeah, unless they measure it. And turns out it's just work, and it's not that hard, and I'm extremely motivated. Did I mention the $60 billion? Here's what I'm actually going to talk about today. Quickly, I got about 20 minutes left. I'll leave some time for questions. I already talked about verified provenance. That's a key part. We're going to go through power analysis, which is wicked cool, and it's what CRI became famous for. Mutual authentication, how it helps. I'm going to talk about proof of work, which is a form of 2-factor authentication. NVM, where all that data is, there's actually ways of doing it correctly and actually making it really hard for the adversary to get all of the bits out of your NVM. And I'm going to talk a little bit about puffs, both weak puffs and strong puffs. Remember, here are the goals for the forward people. That's why it's in purple. Purple, you can't prevent reverse engineering. Your adversary is going to get your part. They're going to reverse engineer it. You can only prevent rapid, easily affordable reverse engineering. You want to force your adversary into a full net list recovery. It's long, it's expensive, it's error-prone, and you want to have to take lots of fibs on a lot of manual electrical measurements. That will delay them, and sometimes delay is the best thing you can achieve. You also want to force your opponent to produce custom silicon, because if you have to produce custom silicon to impersonate a compatible chip for one, you, with limited budget, might go after somebody else. You might go after a different vendor who doesn't require custom silicon. Not all reverse engineering companies, there's 2 or 3, they're totally happy making custom silicon. There's another 9 or 10 that are just going to try to take your code. So if you can force your opponent to produce custom silicon, you're going to eliminate 75% of what we call the cloners before you even start. All right. First one, power analysis side channel. This is incredibly cool because power analysis side channel works basically on the concept that when you're doing crypto inside of a chip, remember how I said that you're causing that, you're doing a challenge and response. You're giving the chip a challenge, and then it's going to perform a compute operation on that data. It's going to combine that with secret keys, and it's going to give a response. So the power consumption of that compute operation is correlated to the secret key material. That's it. That's power analysis side channel. And the reasons why this is true is that, this is the math behind elliptic curve. It's perfect, right? But what's not in the math is that when you actually reduce that to silicon, it's a bunch of gates. Every one of those gates has a power supply connected to it. You won't see a power supply signal in the math of these functions. It's not even, the math is cryptographically correct. It's not electrically correct in a lot of places. So if you, the adversary, have control over the data that the thing is processing with, this is a gift. This is a gift, and an unprotected AES operation, I have to send it about 1,000 random challenges and capture the power supply processing from each of those 1,000, and I have your key. In fact, back in the day, I probably shouldn't say this, but what are they going to do? Back in the day when CRI was getting into the satellite TV space, because they were breaking into these chips really easily by using this technique, CRI would send letters, actual letters printed on a paper going, hey, we looked at your latest design. We believe your current key value is this. And they printed it out in hex. And they're like, we recovered this with power analysis side channel. If you're interested in talking about some effective countermeasures, give us a call. That's just a great letter. Anyway, that's how power analysis side channel works. You, as the adversary, have control over the data causing compute, and you want to work with that. How do you prevent? You can't, well, there's ways of preventing it at the circuit level, but the second part about this is mutual authentication because, again, data is being pulled out of the NVM, secret data, and it's being combined with a challenge, and you're now going to perform a compute on it. Remember that compute operation of circuits. There's an incredible assumption here, and this is why lasers and faults and glitches are so effective, is that if I'm going to actually do an AES operation, let's say, and it takes 14 rounds of compute to finish that, what happens if I only do 2 of those rounds? What happens if you can cause a fault or a glitch that causes that particular control circuit that's saying, no, do all 14. What if you cause it to flip and say, all done, and release the data that's been created by a fault? The algorithm didn't complete at all. Now there is very strong correlation between that return value and the secret key material. So there's something called a differential fault attack. It's also called a bell core attack, where all you're doing is sending challenges and causing corrupted compute and the chip is outputting corrupted compute. Again, do that 100, do that 1,000 times, and you'll have the key value itself. Mutual authentication is a countermeasure for that. When you pull the ID out of the chip also sends the verifier a random number, because why would a chip ever verify? Why would a chip trust its verifier? Verifiers have to prove themselves to the prover, just like the prover has to prove itself to the verifier. You do this at all steps of verification. Nothing should trust anyone. The verifier doesn't trust the chip doesn't trust the verifier. Send it a challenge. And when it sends you back the challenge, the verifier better be able to say, and I know what the correct answer is supposed to be, and they hash it. And they send you a hash of what the correct response, or maybe they send like the lower 32 bits of what the correct answer was supposed to be. So now the secure core is going through and it's checking that, and it now looks at what the verifier actually said, and they're saying, no, I knew what the right answer was supposed to be, and you don't release any data if the verifier can't prove that it already knows the correct answer, because then you're talking to something adversarial. So mutual authentication is a way of preventing harvesting of potentially corrupted compute. And again, please remember, a secure computation is only secure if it completes correctly. And there's a lot of space in that statement for both countermeasures and attacks. All right, proof of work. I love proof of work. Proof of work is very cool. It's a second factor authentication. You can't send, a code to its cell phone. The device doesn't have one, but you can put something else into the part that you're not only proving it knows something, right? It knows the secret value that was programmed in the netlist. It knows the secret value that was programmed into NVM. What you're actually proving also is something that it has. So here's an example of a circuit. And what it's going to do is a very fast compute. It's going to take the challenge in this circuit, and what it's going to do is it's going to take that challenge and it's going to process that challenge with 128 AES operations. So it's going to encrypt, it's going to perform 128 encryptions, and it's going to perform 128 encryptions really quickly. Because if you take that AES circuit and unroll it and make a hardware optimized version, even without DPA protection, it takes about 1.28, about like 1,500 clock cycles to finish that swizzle of the challenge. And then you can compute and send it back. If you don't actually have a fully unrolled AES chip in your compatible, it's going to take you about 41,000 cycles. The verifier should be smart enough that it can actually tell the difference between something that's responding in 1,500 cycles and something that's responding in 41,000. So you start a stopwatch on it inside of the verifier. If the prover cannot respond fast enough, it doesn't have this circuit. So it becomes a two-factor authentication. A verifier can prove that a prover has correct information. It has a proprietary circuit. And this can force your adversary to having to build that circuit into their chip and has to copy your netlist. Yeah, we'll skip that bit. Just in the interest of time, we're going to move that one on. All right, protecting NVM. NVM is great, but There are so many attack surfaces. I'm going to speak about a couple of them pretty quickly. In general, there's usually a big, like flash macro or an MRAM macro or an OTP macro. There's something in your chip. It's provisioned during manufacture and I/O, maybe over the I²C, and the secure core then computes it. You do memory map, you put the secret data in one region, you put like user data so that there's normal there's normal storage that the chip can do. You put user data in another region, and the arbiter is the one handling that. It arbitrates between what's going out to the real world and what's happening in the. This is eminently attackable. And this isn't even without saying, oh, you mentioned the word flash. I can use a scanning electron microscope to pick out the bits in your flash. Yeah, you can, but you don't even need to do that. If I get if I cause a glitch or a fault, Sarnofsky would love this, on the lifecycle control, the chip might think it's now in a manufacturing state. And one of his YouTube videos actually shows this. And then you just go in through the I²C and you start doing readbacks of the data that was provisioned. Easy attack. You can suck out the entire NVM image that way. The other thing I've seen, which is staggeringly cool, you take that NVM macro, usually they're standard IP. If you know the foundry, you know what the pinout on the macro is, you can go into the macro, grab like 2 of the address bits and create new bond paths for them. And now you're actually you do a user read of the user data region, but you, the adversary, have control over the actual address pin. So the read and write happens, but you redirect user-to-reader reads into the secret data region, right? And now the chip thinks everything's fine, except you're now reading user data by a pretty straightforward fib. That one kept us up late at night. Here are the countermeasures for it. Never allowed readback, ever. And there's no reason to allow readback. And you even talk to the test engineers and they're like, what do you mean I can't have readback? You don't need readback. What you need is something that says that the data was stored correctly. So just send back a CRC of it. Do not allow the test engineers to tell you they need to read back when they don't. They need a CRC, and then it's like one more step during manufacturing. They're like, fine, I'll calculate a CRC of what it should have been. Never allow readback data. The other trick that we came up with was secret data. You can see the secure core is like a by 32. User data is all by 8. So all of the circuitry on the user data path is only 8 bits wide. Secret data is the full data width of the memory. And you ignore the rest of the memory. You just throw it out. It is lost. So this is useful because if they do take over user data reads and somehow redirect those addresses, they can only ever get the lower 8 bits of your overall security word. So they might get a quarter of your data, or they get an eighth or a 16th, however many you divide it up by. But you throw out that data and it breaks the 2 paths so that user data is not the same width as the other one. I got a few minutes left. I'm going to get into puffs really quick. Puffs are physically unclonable functions. They're chips that generate their own fingerprint value. They are really they're usually terrifically understood. They're definitely overmarketed. In general, it's a random process. To the puff circuit, it comes up with something. It comes up with an output and then a helper data image that helps stabilize it. Basically, some error correction to make sure that the secret output of a puff is correct and stable for the next 10 years. During regeneration, so enrollment usually happens once. During manufacturing, usually at final test after all the packaging stress is over with. Down in regeneration, the helper data is then loaded in the puff circuit and you get the output back. Here's how it's usually used incorrectly. People are like, oh, it's a puff. The output is unclonable. And like, well, no, the output, nothing is more clonable than a digital value. It's the perfect clone. If you just need to find out what that value is, and then if you're building a compatible, you just hardwire it. And you don't, or pretend it came out of a puff circuit and you just stored it in NVM. There's nothing unclonable about a puff output. The other point is that people are like, well, puffs are better for IoT because it's less expensive in a manufacturing test because you don't have to provision data. So you skip the whole NVM write, you save cost and money. And that's not true at all. Puffs actually take a lot of time during enrollment. And then you have all that helper data image that needs to be programmed anyway. 5 minutes. I can do this in 5 minutes. Here we go. All right. Here's one way to use puffs well. It's a little complicated on the bottom, but it's not terrifically bad. The puff is generating an output, let's say 128-bit output. You program a 128-bit value into NVM memory, and now it's an XOR mask. So this is a form of one-time pad encryption that a chip can actually do. And you can store secret values in a chip, and now if your adversary is going after it, they don't go directly after the NVM. They have to get the data out of NVM, and they have to get the PUF data. With the caveat, again, that the secure core, if it's not protected, if it's actually processing on that, this doesn't matter. Power analysis, fault, glitch, all of that stuff that can go after the compute value can reveal all the secrets that you're trying to protect in that place. The cool thing about PUFs that is different than NVM is that if you turn a chip off, the data is in NVM, and it's just sitting there, and it can be exposed to all kinds of physical attacks. A PUF, however, is an actual mixed signal circuit, which is why it gets a power supply signal in this cartoon. If you turn off the chip, the PUF circuit is not going to work. It has to be powered up in order for it to work, and while it's powered up, you have a whole bunch of anti-tamper detectors and alarms that are protecting you against from actually going after that chip. But if you turn the chip off, there's no anti-tamper detectors anymore. There's no clock signal. There's nothing. You can go after the data that's in NVM. So this is the real advantage that PUFs have versus NVM, is that PUFs will not produce their output unless it's powered up. And when you're powering it up, you can power up protections as well as that. There's a really cool thing about what's actually unclonable about a PUF. Remember that helper data thing that I mentioned? That helper data helps stabilize. Chip 2319's helper data can only be used in chip 2319. And if you take chip 2319's helper data and put it in another chip, you're going to get garbage. You're not going to get the actual value. So it's a chip unique transformation function. So it should physically unclonable function. Unclonable function should be one word. And that's the trick to what PUFs are really good at, because in a way it's a form of challenge response itself. If I gave a chip a helper data image, only an authentic chip is actually going to be able to use that helper data to give me a known output. And you can build some protections around that. Happy to talk about that part offline. The other cool thing about PUFs, and I swear I'm getting close to the end here, there's a type of PUF. Remember how I said alarms and sensors and that kind of stuff isn't so great? One thing you can do, instead of just using a binary output from the sensor saying, hey, someone walked in front of the driveway, what a sensor could actually do is it could be part of a PUF circuit itself, right? And now you're actually going and measuring the integrity of your countermeasure. And if your countermeasure is correct, then the PUF's output value is what it should have been. These are called tamper-evident PUFs. They are surprisingly tricky to get right because you can't use error correction. Because if you did have error correction and your adversary then corrupts it, the error correction is going to fix the corruption and you're going to think everything's fine. So you have to figure out a way of sensing your sensors and coming up with 128 bits value that's nearly exact to what it was before and somehow make use of that in a cryptographic way. And that turns out is a really hard problem. Again, also with the usual caveat that if your adversary goes after the core, game over. All right, I got to my conclusion slide. I'm going to run through it quick. I talked about all 7 of those things. I'm happy to talk about it more. I'm here for another few hours at least, or maybe even till the event tonight. Forward engineering, please remember what the goals are. You're trying to force your adversary to spend money and time on a full net list recovery, lots of fibs, lots of direct electrical measurements. That's the best you can hope for. You can force your opponent to produce custom silicon. They will, in fact, go after another product rather than building custom silicon, because there's a lot of chips that don't need custom silicon to go after. They're going to go after those first. So they might even come after you last, knowing that you just require a custom silicon build. Reverse engineering, keep in mind the goals. If you have expertise in firmware, take the firmware out of the chip and see what secrets are hiding there. If you're an expert in side channels, pull the keys out using side channels. Hook up a scope. You can always see what cryptographic protocols are happening in a scope. You can tell whether it's AES. You can tell if it's elliptic curve. You can tell if there's hashing operation. You can learn the entire protocol that a chip is performing just by watching the power supply noise. If you have that expertise, always use it. Fault is amazing. Fault can eliminate all of the checkers. If you have a checker that's actually monitoring a corruption, that mutual authentication thing, if you have a 2-beam laser, you fault the correction and you fault the checker. And then the data comes out of the chip. And yeah, powerful attack, dual beam, fault attack. I think was going to be a talk later. It's one of the days about that. So I strongly encourage it. That was it. Thank y'all for sitting through that.
All right. Thanks, everybody. What a great talk.
Left.
What a great talk. Excellent. All right, so we have time for 2 questions.
Uh-oh.
Sammy.
Hey, great talk. Thanks.
Thanks.
On the CRC protection slide, could an attacker do a CRC readout at byte 0 and then do a CRC readout at byte 1? So they're getting CRCs of overlapping information. If you produce 2 tables, you know that only one byte you'll have like overlapping data.
Right. No, that's a really good point. And that's one of the limitations of the CRC is A, the size of the CRC, and B, the granularity of the access. Yes. So typically what we have done, and we protect a burst of reads during manufacturing. So you write, and then you CRC. So you have to, carefully manage the burst size and the granularity of that. 100%.
All right. One more question. Anybody? Going once? Going twice?
Ed's got a question.
Ed's got a question?
Ed's always got a
question. Oh, Ed's got a question. All right, great.
What I do for a living. You talk a lot about what's going on in the security in a chip. What's changing, though, is that we now have multiple chips, multiple chiplets.
Oh, yeah.
We have AI chips coming in there, which are going to be changing all the time with the algorithms that are going to be constantly updating.
Yep.
How does that change what you're doing in security?
Next question, please. Chiplets are amazing. For those of you who don't know, chiplets is usually one chip inside of a package. It's how we've done things for a long time, except when we were doing multi-chip modules for that very brief period of time when we thought that was cool. Or system in package. Been to a lot of those conferences as well. It's coming back. There's a lot, but they're coming back for reasons that chips are larger now than the reticle, that you can actually print a single die. Remember that wafer, like the maximum size is like 25 square millimeters. Suppose you want more. Now you have to put 2 chips into the same package and connect them up. So there's a lot of chips that are coming out now with this homogeneous chiplet approach, especially for AI kind of compute systems. And there's strong interest in the defense community also about chiplets. What gets weird about that is who's the verifier now, right? If all of them are identical and they all have some sort of, who do you trust in that setup? And I don't think anyone really has an answer yet. I think there's a lot of point solutions. We have our ideas. Our customers certainly have their ideas about how do you declare who the trust is. And what if things start going heterogeneous, right? Which is what the Defense Department wants, which is I have a root of security chiplet, I have an IO chiplet, I have an HBM chiplet, I have a root of performance chiplet, and I'm going to assemble all of those from 12 different vendors. What was the supply chain, controls at all 12 of those vendors, right? So it scales linearly. So as I said earlier, I don't believe in hardware Trojans for monolithic solutions. I totally believe in hardware Trojans in a chiplet-based environment. And the answer is, to get all back to that, is where this presentation started, that it needs much tighter control over the supply chain so you can quantify what the provenance of all these chips is. And if you have a chiplet in your MCM and you can't prove the provenance, the verifiable provenance of that, you're just asking for trouble on that. So I think monolithically, there's very few companies in the world that can actually print a 25 square millimeter chip, in a state-of-the-art node. That's $100 million investment, to start, to even print that first chip. There's very few companies that can do that. I'm not as worried about hardware Trojans in that capacity, but when you get down to chiplets and complex, especially AI, things that scale horizontally, supply chain security, I think, is going to become a lot more important in a heterogeneous environment. That's my opinion. Cool.
All right. Thank you so much.
Thanks, everyone. Appreciate it.
Big round of applause.